Right. Okay. So, yeah, let me take this out here. Yeah. So, we're talking about right angle triangles, and the ratios. So katoa, right? So katoa. Now, um, we have two things. We have reciprocals and inverses. They are different things. A reciprocal is where we swap the numerator and denominator. So if you swap the numerator and denominator here, you'll get 1 over sine of theta. If you look at cos of theta, if you swap the numerator and the denominator, you get 1 over cos of theta. If you look at tan of theta, if you swap the numerator and the denominator, you get 1 over tan of theta. And so what these simplify down to, we give it one name. This will be cosec of theta, this will be sec of theta, and this will be cot of theta, right? The way you remember it is look at the third letters, right? S, C, T, S, C, T. Okay, so that's the reciprocals. When you talk about an inverse, exactly as we did with solving of equations, we spoke about additive inverse, multiplicative inverse. Like if you said 2x is equal to 1, to solve for x, you divide by 2 on both sides. So now here, if I want to solve for if I want to solve for theta, how do I solve for theta? You take the inverse of sine on both sides. So now we say sine to the negative 1, cos to the negative 1, tan to the negative 1. So we call this here arc sine, arc cos, and arc tan. Right, what this would do is it'll enable us to solve for theta. So basically, it'll be like sine of theta is equal to 1 over 2. But if I take the arc sine on both sides, and I'll have theta is equal to arc sine or sine to the negative 1 of half. So that's the inverse. So in essence, the reciprocal ratios are used to simplify. They are used to simplify, re-express something, right? But when you're talking about the inverse ratios like these are used to solve, right? To solve for what specifically? Theta, right? So that's that. But exactly as I said, now we have a limitation with this. The limitation is that we can't solve for angles that are bigger than 90. So what we do is we make use of a Cartesian plane. But if you make use of a Cartesian plane, there's a problem with that. When you use a Cartesian plane, if you had a triangle on your page, that triangle is just on your page. We don't know precisely where it is. But as soon as you bring a Cartesian plane into the question, now we talk about magnitude and direction. So magnitude means how much, direction means where to. And so if I have this point here and I call this here 2 units and 1 unit, right? Listen to this, 2 units and 1 unit. We can't just say that this is 2 units and 1 unit because that's only talking about magnitude, how much. We have to say plus 1 and plus 2. This is why whenever you, in any specific quadrant, you have to say plus or minus because then it'll tell you where about you are specifically. Trust me, this is going to link to something that we're going to talk about when we solve the problem. So you need to pay attention to this. So when we say plus 2, we're saying that we're moving to the right. That's what the positive means on the x-axis. Because if it was negative on the x-axis, that means we're moving to the left from the origin. Here we're saying we're moving from the or to the right from the origin, but by how much is the magnitude? 2 units. So we're moving to the left where, we're moving to the right where, but by how much? 2 units. We're moving up where, direction, by how much? 1 unit. You have to state both magnitude and direction. And so whenever you're given the Cartesian plane, you always need to remember magnitude, direction, or you remember sign number, sign number, sign number. That's what you need to remember all of the time, right? But anyways, that's that story now. We just need to keep that at the back of our mind because we know the Cartesian plane helps us to orientate things in space. That's the essence of it. The primary purpose of the Cartesian plane is to solve for angles that are um bigger than 90. So let's say we have this line here, and they say, okay, use the techniques of trigonometry to find out what this theta is here. It's an angle that is not less than 90, now it's bigger than 90. And so the way you would do that now is you would see take a line, right? Locate that point, take a line and draw it vertically to the x-axis, right? And then what we'll do is to find this angle here. See this angle here? This is what we call the angle in the standard position, right? So it's angle in the standard position because it takes you from the x-axis to the terminal ray. So this is a theta 2. It's a quadrant 2 angle, right? And so what we'll do is we have to first, this is where it's so important. You have to first find what we call the reference angle. That's extremely important. So to get the angle in the standard position, we must first find the reference angle. And so what's the reference angle? If I do it like this here, This is a right angle triangle in quadrant 1, a right angle triangle in quadrant 2, quadrant 3, and quadrant 4. The reference angle is the smallest positive angle from the x-axis. See, smallest positive, that's one there. Smallest positive, that one there. Smallest positive, that one there. Smallest positive, that one there. Can you see that? So all these angles here are what we call reference angles. And so if we can find the reference angle, right, watch here, if I can find this reference angle here, then I'll say 180 degrees minus the reference angle will give me quadrant 2 angle, which is the angle in the standard position. So it's literally that simple, right? But it goes a step further, right? It goes a step further. So let me come down here. Exactly as I just stated now, you have the Cartesian plane, magnitude and direction is compulsory, right? So let's first talk about solving for angles. Then we'll talk about solving for sides. If you're solving for angles, exactly as I just stated, when you're solving for angles bigger than 90, we need the reference angle, and then we'll either add or subtract by 180 to get the angle in the standard position. So like this case here, I want to find quadrant theta 2, but I need to first find out what's theta reference. But how do we find the reference angle? It's not as straightforward as we think it is. See, theta 2, or theta reference is here. What are we given? We're given opposite and adjacent. So we'll say tan of theta reference is equal to opposite over adjacent. You can see I did not take the side with the direction. I took only the magnitude of the side. So that's the rule you need to remember. To find the reference angle, you take the magnitude of the side. When you solve for theta reference, whatever that works out to be, how do we solve for theta reference? We make use of the inverse. So it'll be 4 over 3, which will be 53.13 degrees. So that's this angle here. What do I need to do? I say, okay, 180 degrees minus 53.13 will give me whatever that theta 2 is. So theta 2 is equal to 180 degrees minus 53.13 degrees, and that'll give me an answer, right? The same idea applies if you have an example like this here. If you have an example like this here now, and I call this here -4 and -3 here, same idea would apply. There's theta reference here. It'll be tan of theta reference is equal to an opposite 4 over 3. Do not take the direction of the side. Take only the magnitude. Solve for this here. What does it give me? 53,13. But now to get this quadrant angle, quadrant 3 angle here, so from the initial ray all the way down here, what do I need to do? I have to say 180 degrees plus 53,13 degrees. And that's how I'll get the angle in the standard position, right? Here as well, same story. If I have a point here, I call that there -4 and 3 here. I got theta here. I'll say tan of theta reference. Now, it has to be the reference angle is equal to opposite 4 over 3, which will equal to 53,13, right? That's 53,13 there. So what I can say is 360 degrees is there, minus whatever the theta reference is here. It'll take out all of this parts here, and it'll bring the arrow right here. So from there to there, you'll find out what that quadrant 4 angle is now. Can you see that? So quadrant 2, I did one with quadrant 3, now I did one with quadrant 4. It's literally that simple. Now with quadrant 1, we don't have to worry because, think about it, in quadrant 1, if that is 4 and that is 3, if this is theta reference, then that's also equal to theta 1, right? Because this is an acute angle. So you're just taking the magnitude of the sides. There's no direction now. Remember, it's both positive. So it's that simple, right? So that's to find the angle. To find the angle in the standard position, you have to use the reference angle. Please, any other way will not work. You have to stick to this. This is the only way, right? Any other way is just not going to work. Right, now, so that's for the angles. Let's talk about the sides, right? Because if you're using trigonometry, that enables you to solve for angles and also sides. So if we're trying to solve for sides, here's the story here now. I have this point here. It's -4 units away from the x-axis. So it's minus going in the left to the left by how much? By 4 units, right? So that's that point there. I want to find out how far down this point lies. So y, I want to find out what y is. Now I can do one of two things. I could use the reference angle or I could use the angle in the standard position. So if I use the reference angle, what relates the opposite side to the adjacent side? It's the tan. So I'll say tan of theta reference is equal to opposite y over, now I can't say minus 4, right? Because if I'm using the reference angle, when we use the reference angle, what did we use? The magnitude of the sides. So we have to use the magnitude of the sides. Can you see that? And if we solve for this, theta reference is equal to, what does this work out to be? It will be, no, sorry, if you have to work this out here now, if you have to work this out, we got theta reference to be what, 36.87. So I'll say tan of 36.87, tan of 36.87 degrees is equal to y over 4. Y is equal to 4 times tan of 36.87 degrees. Right, and if you solve for this here now, let's see what we get. 4 times tan of 36.87, that gives me 3. Can you see that? So how down, what's the magnitude of it? It's 3. 3. But remember, we're talking about what? The Cartesian plane. So therefore, y is equal to minus 3. Can you see that? But because we're using the reference angle, it'll only spit out magnitude values, right? It'll only spit out magnitude. You can't go put minus 4 here and solve it. It will not work. Because when we use the reference angle, we use the magnitude of the sides and not the sides with the direction. Please do not do it any other way. This is the only way. This is the rule. This is the rule best by practice. Doing the hundreds of questions, this is the rule. The rule is when you're using the reference angle, you only put magnitudes of the sides. So the answer that you'll get here will be a magnitude, which is 3. But because we're talking about the Cartesian plane, we need to mention where about. So minus 3 will mean going down by 3 units. Okay, so that's that. Or alternatively, let me just keep that there. Alternatively, I could use the angle in the standard position. If I use the angle in the standard position, so it'll be tan of theta 3 is equal to y over, now I can use that minus 4. Because the angle in the standard position tells you precisely where that point lies. It lies precisely there. See, this theta reference just says it lies there, like that. It's just randomly. We don't know exactly from the starting point to the end point. We just know in that small gap, as if we're just dealing with a triangle like this here. So that's where the angle in the standard position locates it precisely. So if it locates it precisely, it'll give you both the magnitude and the direction. Here, with the reference angle, it doesn't locate it precisely. It just gives you magnitude, right? Here, it gives you both magnitude and direction. So therefore, I use it with the direction. And if I solve for this here now, I'll get tan of 216.87 degrees equal to y over minus 4. Y is equal to minus 4 multiplied by tan of 216.87 degrees, which is equal to let's do that. Minus 4 multiplied by tan of 216.87 degrees. And that gives me minus 3. So what can you see why I gave you minus 3 now? Because we're using the angle in the standard position. So it gives you the answer with both magnitude and direction. Here with the reference angle, it does not. Please, Sumesh, do not over question it. This is the rule. You cannot think of it in any other way but this way, right? So this is the rule. Using the reference angle, use magnitude of the sides. So what you get here will be the magnitude. Using the angle in the standard position, you have to use the sides with the magnitude and the direction. So when you solve it, you'll get an answer that gives you the magnitude and the direction. Right. So that's that. Now let's go and solve some papers. Okay, yeah, okay, we can even do this here. Let's talk about the application aspect of it. So that's from here now, right? The application, where we can use it in the real world. So the application is very simple. If you have sine of theta is equal to opposite over hypotenuse, then it's very simple. If you have an angle and you have one side, then you can find the other angle, right? Or if you have two sides, then you can find the angle. But they are just listed out here a bit more strategically. I said if you're finding a missing side, you need a right angle triangle. That's the whole idea of trigonometry. You need one angle and you need one side, right? And then if you're finding for a missing angle, you need two sides, right, to solve for that missing angle. And then you just need to ask yourself, okay, what ratio will link the given side to the unknown side? Then that you'll see in this case here, it's cos. Here you'll have to ask yourself, what ratio will link both the sides to this angle? What's that answer? Tan. Right, that's the question that you ask yourself, the way you frame the question. Right, so let's solve some questions here. Yeah. See, here we're given a triangle that's just randomly in space. There's no Cartesian plane. It's just random in space. So let's do this. There's theta here. this is P, that is S, and this is Q. If I'm looking at this here now, I'll say, okay, tan of theta is what? Opposite over adjacent. So therefore, let's just do this. So, ka, toa, right? So it's opposite over adjacent, which is equal to S over Q. See, sine of theta is what? Opposite over hypotenuse. So S over P. So it'll be S over P, but that minus sign there has to come there. Right? So remember, what we are doing here now is we are not solving, we're not doing anything but simplifying. Tan of theta is the same as S over Q. Sine of theta is the same as S over P. Now we are merely just simplifying. We're not solving for any angle. We're not solving for any side. So these ideas here now, we don't have to even think of any of this here because we're not solving for anything. We are simplifying. Right? Please keep that distinction in your mind. Here now, see, sec squared of theta, this is a reciprocal ratio. Why do we use reciprocal ratios? To simplify. So to simplify, it'll be 1 over cos squared theta, right? But cos squared is what? But cos of theta is what? Q over P. So it'll be 1 over Q over P squared, which will be P squared over Q squared. Right? Same thing, we just simplify. Re-express this as a ratio. Re-express this as a ratio. This is why we call it trigonometric ratios, because this here is a ratio. This here is a ratio. This here is a ratio of two sides. Right? That's the definition of it. Right? If you have to solve this one here quickly, this is like calculator skills. So we have if A is equal to 20 degrees and B is equal to 50 degrees, use your calculator to evaluate this to two decimal places. So very simple stuff. You'll just say sine into 20 plus 55. Remember, see that D there at the top means it's in the degree mode, right? Because we know we don't put symbols here. We don't put the degree symbol here, right? So where it is coming from, it's there. The D there is putting the degree there, right? And so this will be 0.97. 0.97. Remember, you can't put units here. It's unitless. Think about it. Because if I have sine of 30 degrees is equal to 1 over 2. If there are centimeters and centimeters, then centimeter and centimeter will cancel. So that's how we say it is unitless. Okay, tan squared of B will be the same as, so we put this into the calculator. Tan squared of B is 55 degrees. Right, and we solve that, we get 2,04. So that'll be 2,04. Here now we have to take this here and re-express it as sine, cos, and tan because we don't have cosec, sec, and cot on our calculator. So this will be 2 multiplied by 1 over sine of A. Can you see that? Because the third letter is a S there. Plus sine multiplied by 5 times B. Put this into the calculator. Straightforward stuff. You're getting easy free marks here, which will be 2 over sine of A is 20 degrees plus sine of 5 times B, which is 55. Right? Then you get 4,85. 4,85. Now please round up to two decimal places. Right, Sumesh, here, this is very simple now. We're talking about, without the use of a calculator, surely we're working and determine the value of this. So how are we going to do this? We can see that these are special angles. So we're going to draw the special angle, triangle. So we're going to do this. There's one triangle here, the 45 degree, 90, and 45 degree here. And then we have the 30 degree, 90 degree, and 60 degree triangle. This will be 1, 1, square root of 2. This one here will be 1, 2, square root of 3. Right? Whatever method you all learned, you can stick to it, right? Sine of 45 degrees. Re-express sine of 45 as a ratio. Sine of 45 will be 1 over root 2. Right? So it'll be 1 over root 2. Put that in brackets. Tan squared of 60. Where's 60 degrees? It's here. Tan is what? Opposite over adjacent, which will be root 3 over 1. But because we're squaring it, it'll be root 3 squared. Right. Cos of 45. Cos will be 1. It'll be the adjacent over the hypotenuse. So 1 over root 2. So it'll be 1 over root 2 there. And plus sine of 30 degrees is half. So it'll be 1 over. So the opposite over the hypotenuse, half. See, that and that cancels. So we're left to 3 plus 1 over 2, which is equal to 7 over 2. Right? 7 over 2. So that's straightforward there, right? So yeah, that's that part, right? So we got that there. Now let's talk about this here. Now we bring in the Cartesian plane in now. Can you see that? Cartesian plane, direction, and magnitude. Just keep that. You have to keep that at the back of your mind. Right? Direction, magnitude. So B has is the point X and 5 lies on the Cartesian plane. It is given that OB, so OB is 13 units, and BOX, so BO and X, it's this angle here, is theta. So what angle is this? This is the angle in the standard position, right? But we're not solving for any angles. They didn't tell us to solve for angles. They just want us to re-express stuff. They want us to simplify. We're not solving. So we don't use any of those frameworks. So how do we do this? If we look at this here, to determine the value of X, if I drop a vertical line down, we have a right angle triangle, right? We have a right angle triangle. So how does it go? It goes like this here. R squared is equal to X squared plus Y squared, right? R is this radius, X is this value here, and Y is this value here. So therefore, we're trying to solve for X. So X squared is equal to R squared minus Y squared. R squared is 13 squared minus Y squared is 5 squared. And so if we solve, that's X squared, right? If we solve for X is equal to plus or minus the square root of. Whenever you are using the square root, make sure you put the plus or minus sign, right? And you can see why the magnitude and direction thing becomes so important here. So it'll be plus or minus. What does this work out to be? Let me just scroll down here. Works out to be plus or minus 12, right? It works out to be plus or minus 12. Can you see why this is so important, Sumesh? The plus or minus. Because X is in quadrant 2, we have to say that X has to be less than 0. So therefore, X is equal to minus 12. What is cos of theta equal to? So there's angle in the standard position. Cos will be the adjacent over the hypotenuse. So it's the adjacent over the hypotenuse, which is equal to minus 12. Can you see? Angle in the standard position, take this sides with the magnitude and the direction. See, that's the negative. So that's why I take it with the minus 12. If they're talking about this angle here now, that's a different story. You'll say 5 over 12. Right? Know the difference there. Here as well. See, 12 over. Sine of this angle is equal to opposite of hypotenuse. See, plus, so it'll be 5 over 13. The 5 is positive. Cos is equal to what now? Cos is equal to minus 12 over 13. Because we're using the angle in the standard position, take it with the magnitude and the direction. So minus 12 over 13. If we simplify this now, we'll have 12 multiplied by 5 over 13 multiplied by the reciprocal, so it'll be 13 over minus 12. That 13 and that 13 will cancel, 12 and 12 will cancel, so we're left with minus 5. Right. Simple stuff there. Here we use the calculator, so let's put this here, calculator skills. So it'll be cos of 2 times 21 degrees. Right, if we solve there, we got 0.74, 0.74. Here as well, we can say sine of x plus y. So it'll be sine of 20 degrees plus 21 degrees gives me 0.66. And if you look at sec, that is 1 over cos, isn't it? So it'll be 1 over cos of 20 degrees, which gives me 1.06. This is equal to 1.06, right? So that's how we solve for those three, just using the calculator. Yeah, this is a very simple one now, because we're using what? The special angles, right? So if we do that now, we got two triangles, the 45 degree, 90, and 45 degree, and then we have the 30 degree, 60 degree, and 90. 1, 2 root 3, 1, 1 root 2, right? Sine square of 45 degrees will be 1 over root 2 squared minus cos of 60 degrees is adjacent over the hypotenuse, which is half, plus, see, tan of 10 degrees multiplied by cot of 10 degrees is tan of 10 degrees over, see, tan of 10 degrees over tan of 10 degrees. Because see, cot is 1 over 10. So that there will simplify down to 1. Right, so now we have half minus half plus 1 will be equal to half minus half, or plus half minus half, sorry. Plus half minus half is 0, plus 1, the answer is 1. So that's how we get that answer there. Very simple stuff. Here as well, to solve, what do we have to make the subject of the formula? x, isn't it? So if we do that now, let's do that. It'll be 1 over 3 sine of x is equal to 2. Make sine x a subject of the formula. We'll multiply by sine x on both sides, and we'll divide by 2 on both sides. So it'll be 1 over 6 is equal to sine of x. How do you solve for x? Make use of the inverse of sine. So it'll be arc sine, isn't it? Or sine inverse. So it'll be x is equal to sine inverse of sine of 1 over 6. And therefore, if we solve for this, it'll be shift sine 1 over 6. And we'll get an answer 9,59 degrees. Right, 9,59 degrees. Right, so that's how we solve for that one there. And it does make sense because x has to be in the first quadrant. So it's a quadrant 1 angle. I can get a bit more in depth here on these questions, but let's work. After term 3, I'll come back and I'll tell you the deeper story of it. Right, here as well, let's talk about it. We're talking about what? The Cartesian plane. Therefore, we need to talk about magnitude and direction if necessary. Right, in the diagram below, Q is a point in quadrant 2. So Q is a point in quadrant 2. ROQ is equal to theta. So that's the angle in the standard position. Okay, and 13 sine of theta is equal to 12. So if 13 sine of theta is equal to 12, then sine of theta is equal to 12 over 13. But sine of theta is equal to, remember this one, you shade your rear, cos x raise tan your exterior. Right, so when you're working with the Cartesian plane, this is what we work with. But if you're working with any random triangle, then we work with SOHCAHTOA, right? So if you're working with this here, it'll be y over r. So 12 over 13 is the same as y over r. So what is y? 12. What is r? 13. So we need to solve for x, right? As the first question states here. So determine the value of x. X squared is equal to r squared minus y squared. Right? Just call that their theorem of Pythagoras. Please, we have to write their theorem of Pythagoras. Right? Exactly. It's a geometry concept. So we have to write the reasoning with it. Right, Sumesh? Therefore, x is equal to plus or minus the square root of 13 squared minus 12 squared. And that will give us some answer. But then x has to be negative. Right? So let's check what that answer is. The square root of 13 squared minus, I think it's like, what, 10, I think. Or 5, right, 5. So I'll give you minus 5. So x is equal to minus 5. Right? Why are we taking the negative solution? Because x is in quadrant 2. Right? You must state that. And obviously a reasoning there for theorem of Pythagoras. Okay, sec of theta is equal to 1 over cos of theta. Cos of theta, remember, cos of theta is cos of the angle in the standard position. So we have to take this here with the negative. So this is equal to 1 over, it'll be x over r. So minus 5 over 13, but we'll swap it now because we're saying 1 divided by that is the same as 1 times the reciprocal of the denominator, which will be 13 over minus 5. So that's how we solve there. Right. Yeah.